Okay, welcome back to science. Today we're going to explore Charles's law. Now, yesterday, just a quick review, we discussed Boyle's law. In Boyle's law, Boyle worked with gases at a constant temperature, and basically he said if you increase the pressure on the gas, it'll compress, and if you decrease the pressure on the gas, it will expand. So you can add pressure and squeeze it into a smaller space, or you can let the pressure off and it'll expand into a bigger space. Now, Charles worked a constant, it says constant pressure, the temperature of a gas will increase as the volume increases, and as the temperature of a gas decreases, the volume will decrease. So in real simple terms, this is saying a gas expands when heated. And you should be thinking to yourself, where have I heard about that before? Things expand when they get heated. This is another example of thermal expansion. So basically what it's saying is you heat up the gas, particles gain energy. As they gain more energy, they move faster. As they move faster, they punch into the side of their container harder, and they make the container get bigger. So I put two little, balloons here in the notes, and one of them I said is cool, and one of them I said is hot. And when Charles said at constant pressure, he meant the air pressure in the room outside the balloon. So yesterday we looked at that slide I had, and we talked about air pressure, and air pressure came from the weight of the air above us. So it's all around us in the room. So it's all around these balloons. It's pushing in on the balloon. So when he says at constant pressure right here, he means this outside pressure on the balloon. That's not going to be changing. And it says as the temperature is increased, the volume increases. So as we warm it up, it's going to expand. Now, yesterday we said, if you see this on a test, you can't figure out whose law it was. Charles changed the temperature, okay, and Boyle didn't boil. So I always remember Charles changed and Boyle didn't boil. So basically what Charles is saying is that as the temperature goes down, the volume will go down. So earlier in the unit we saw that example where they stuck that piece of brass in the liquid nitrogen. When it got cold, it got smaller because the particles moved slower and they took up less space. And the same thing is happening with this gas. As you cool the gas down and the temperature goes down, the volume goes down. And as you heat the gas, the volume goes up, which over here in this diagram with these balloons, I have a lowercase t to indicate a low temperature and a little lowercase v to have a little small volume. And when we increase the temperature, I got this uppercase T, and as the temperature increases, the volume is also going to increase. Now, Charles's law predicted that the volume of a gas would be zero at a temperature called absolute zero. And it was actually another scientist, Lord Kelvin, who wanted to test this out. So he said, well, what happens if we remove heat from an object? And can we just keep removing heat? And eventually he came up with the idea that if the temperature was, the motion of the particles would essentially stop. Get into a little area of quantum physics where you can't ever predict the location of a particle. And so if it stopped, you would know where it's at, so it kind of violates that. Also, when you try and remove all the heat from something, in order to be able to do that, you actually need something colder than that to move the heat to. And since absolute zero is the absolute coldest temperature that is theoretically possible, we're not able to do it on Earth. We can get to within a fraction of a degree, but there's always some way for the heat to get in. But what Charles's law says, it says it predicts the volume of the gas would be zero at a temperature called absolute zero. So basically what he's saying is if the particles stopped moving, they wouldn't take up any more space. And the volume would go to zero. So I'm going to take a look at these slides, and we'll think about some of this in a different way. And here's a graph of Boyle's law, and it shows here where the pressure is really high, so it's at 100, the volume is small, it's at 60. When the pressure is lowered and the pressure is 60, the volume is high and it's 100. So as the pressure goes up, the volume is going down. And so we say this is inversely proportional. So we start off with, if we look and we have a pressure of 60, the volume is big. And when the pressure is 70, the volume is smaller. When the pressure is 80, the volume is still smaller. When the pressure is 90, the volume is still smaller. Finally, when the pressure is 100, okay, the volume is smaller. So what we're saying is, as you put pressure on something and you squeeze it, it's going to fit into a smaller space. Okay? The graph looks more complicated than the idea really is. With a plunger yesterday, you can push down on it, add more pressure, and it squeezes it into a smaller space. Now, Charles's law shows that as the temperature goes up, the volume goes up. Or as we're lowering the temperature, the volume goes down. When people do experiments like this, the data falls into a straight line. So it's pretty easy to extend the line down, and this is basically what Kelvin and Charles did, it's called extrapolation. So, in the range where we can do experiments at the temperatures we can reach, we see that the data is falling in a straight line, so you can extend it on down. In algebra, this would be called the y-intercept, and you find the temperature where the volume is 0, the temperature would be 0, okay? And that's the temperature Lord Kelvin called absolute 0, because it was absolutely the coldest temperature where the particles stopped moving. And remember, the measure of heat is the average kinetic energy of the particles. So if the particles have no more kinetic energy, they have no more heat, so they have no more temperature, so that would be the coldest possible temperature. Now, here's a picture of somehow how you'll see Boyle's law. And what this is showing us is that as the pressure increases, so the pressure is coming on this plunger. Now, one of the things that this sometimes confuses kids before I explain this, okay, this is a cutaway. You're supposed to imagine that this thing is, completely whole. And so they've cut away so we can pretend like we can look to the inside of this thing. So they've got this gas inside this cylinder, and there's a plunger on top like a piston, and then it's going to push down. So, and this is really simple to understand. When there's a small amount of pressure pushing on it, the gas is taking up a big space. And then instead of having one weight, you have two weights, and it squeezes it down. This is like yesterday's video where I pushed down on the syringe plunger with his hand. And then if you add more pressure where they have four weights, then the gas will compress into a smaller space. So basically they're the same as you push down on this thing harder and harder and harder, and the volume of the gas will go down, which is what Boyle's law said. As the pressure increases, the volume will decrease. So the volume was big, and now the volume is small. The pressure was small up here, and the volume was big, and down here where there's four weights, the volume is small. So as you add more weights, the volume goes down. As you remove weights, the volume goes up. And the weights represent the pressure. Charles's law says that as we heat the gas, and again, you're supposed to imagine that this is whole, but we're looking inside. And I also said when you see gas particles, there'll always be some indication of how fast they're moving. So here they have blue and small little tails like comets, and here it's yellow, which is a warmer color. So it's supposed to tell us that this is warmer and the tails are bigger. So it's supposed to tell us that the gas particles are moving faster. So we know as you add thermal energy to something, particles speed up. So the same when we get to minus 65, so particles are kind of cold, they're not moving very fast, they're not doing much. And we heat them up to 250 degrees, they have a lot more energy and they move faster. Well, because they're moving faster, they're going to slam into the top of the piston harder, and they're going to take up more space. So this is an example. Basically, we can think of it as being thermal expansion. As we heat it up, it expands. And then, of course, as we cool it down, it would condense and take up less space. Okay. Now, the other thing that happens, in this case, the plunger can move up and the gas can expand. Okay, so another example like this would be, it's in the wintertime, if you go into a store and you buy one of those like helium balloons, you know, that people get for birthdays or whatever, and it's inside the store where it's warm like this, it's big, and when you take it outside, it's really cold in the winter, like it's freezing temperatures, it'll get really small outside. When you bring it back inside, it'll re-expand. So this is the case. This case, the size of the container is able to change. But what happens if the container can't change? So when it's cold, you would have low pressure inside the container, and so the particles would be moving slow and they would bump into the sides of the container. There wouldn't be very much pressure. Here, when we heat it up in the gas inside of a container that can't change temperature, then the pressure inside the container is going to go up. So an example of this in real life would be like car tires. If it's in the winter or in the summer, and you come out and it's been a cool night, and you check the air pressure of the tires in the morning, it'll be low. Now, if you're going on a long trip and the road is black and it gets really, really hot, as you ride across the hot road for a long time, the tires are going to warm up, the air inside the tires is going to warm up, and the pressure inside the tire is going to go up. And this is why sometimes on the interstates, you'll see, like, it looks like a tire just completely exploded and blew up, and there's just pieces of rubber all over the place. Probably what happened was the air pressure was fine in the morning, is that person, trucker or whoever, rode across the interstate during the day and the pressure in the tire went up. Eventually it went so high that it blew up the tire. This is another example of Boyle's law. We add pressure to the gas, by increasing how hard it's being pushed down, the volume goes down. This is a graph of Charles's law. So it shows down here the volume would be 0 at a very cold temperature, and absolute 0 is negative 273. And as we heat it, the gas is expanding. So it shows we heat it at this temperature. It's got constant pressure because the weight isn't changing. The volume of the gas increases as the temperature goes up. This would be another example of Boyle's law. You have a force of 1 kilogram here, and you have a pressure of 2 kilograms here. When the pressure went up, the volume went down. And it shows the temperature is being constant. These might be the kind of pictures you might see on a test. Okay. Ask yourself, whose law is this? Well, it shows at constant pressure, both of them have 1 kilogram. As the substance warmed, it expanded. So this would be Charles's law. Okay. Now, there's more than one temperature scale. Okay. Normally, we deal with Celsius, and this is what most people in the world use for their daily temperatures, and the Celsius scale came up first. Okay. Lord Kelvin worked with his scale after this when he was working with things that were really cold and asking himself about heat and what would happen if you removed all the heat. So absolute 0 on the Kelvin scale, on the Celsius scale, is negative 273 degrees. We know that the freezing point of water is 0, and 100 degrees later is the boiling point of water. Now, Lord Kelvin, when he was working with the Kelvin scale, said, okay, well, if this is the coldest possible temperature where the particles are going to stop moving and there's no more heat, then that would be 0. It's the coldest possible temperature. So he made absolute 0, 0 on his scale. These two scales are both metric scales. They're both SI units. So the amount of degrees is exactly the same. So from negative 273 to 0, you have to go up 273 degrees. So it's the same number of degrees from absolute 0 to the freezing point of water. On the absolute scale, you add 273 degrees, and you get to the freezing point of water. So just like you add another 100 degrees to get to the boiling point of water, the boiling point of water on the Kelvin scale is 373 degrees. You're going to answer these questions on your own, and then we'll take a look at the answers on the next video.